last time we had seen that a matrix can be written basically, let me draw here the matrix. So we had several rows, right? And then we multiply usually this one by one column, right? And so whenever we multiply these guys, you can see these as two different equivalent types of representation. Can you see, right? You don't, is it legible? Can you, okay. So you can see basically as the output of this product as being a sequence of like the first row times this column vector, and then again, I'm just, okay, shrinking them. They should be the same size, right? Because otherwise you can't multiply them. So you have this one and so on, right, until the last one. And this is going to be my final vector. And we have seen that each of these bodies here, what are these? Talk to me, please. Those are scalar products, right? But what do they represent? What is it? How can we call it? What's another name for calling a scalar product? I showed you last time a demonstration with some trigonometry, right? What is it? So this is or the projection if you talk about geometry, or you can think about this as an unnormalized cosine value, right? And so this one is going to be my projection, basically, of one kernel, or my input signal onto the kernel, right? So these are projections. Projection. All right. And so then there was also another interpretation of this, like there's another way of seeing this, which was what? Basically, we had the first column of the matrix A multiplied by the first element of the x of this vector, right? So element number 1. Then you had the second column times the second element of the x vector until you get to the last column, right? Times the last n element, right? Suppose that this is long n, and this is m times n, right? So the height, again, is going to be the dimension towards we shoot to, and the width of a matrix is the dimension where we're coming from. Second part was the following. So we said, instead of using this matrix here, since we are doing convolutions, because we'd like to exploit sparsity, stationarity, and compositionality of the data, we still use the same matrix here, perhaps, right? We use the same guy here, but then those kernels, we are going to be using them over and over again, the same kernel across the whole signal, right? So in this case, the width of this matrix is no longer n, as it was here. It's going to be k, which is going to be the kernel size, right? So here I'm going to be drawing my thinner matrix, and this one is going to be k, lowercase k, and the height, maybe we can still call it m, okay? All right, so let's say here I have several kernels. For example, I may have my cyan kernel, then I may have my, I don't know, green. Let me change. Let's put pink. So you have this one, and then you may have a green one, right? And so on. So how do we use these kernels right now? So we basically can use these kernels by stacking them and shifting them a little bit, right? So we get the first kernel out of here, and then you're gonna get basically, you get the first guy here, then you shift it, you shift it, you shift it, and so on, right? Until you get the whole matrix. And we were putting a 0 here and a 0 here, right? This is just recap. And then you have this one for the blue color. Then you do magic here. You just do copy, and then you do paste. And then you can also do color. See? Fantastic. Magic. And we have pink one. And then you have the last one, right? Can I do the same? Copy. Yes, I can do. Fantastic. Sorry, you cannot do copy and paste on the paper. All right, color. And the last one, light green. Okay. All right, so we just duplicate. How many matrices do we have now? How many layers? No, don't count the number. Like there are letters on the screen. M. K or M? What is it? What is K? Decide. You're just guessing. You shouldn't be guessing. You should tell me the correct answer, right? Think about this as a job interview. I'm training you. So how many maps do we have? M, right? So these one here are as many as my M, which is the number of rows of this initial thing over here, right? All right. So what is instead the width of this little kernel here? K, right? Okay. What is the height of this matrix? What is the height of the matrix? Are you sure? Try again. I can't hear. N minus k plus 1. Okay. And the final, what is the output of this thing, right? So the output is going to be one vector, which is going to be of height the same, right? N minus k plus 1. And then, it should be correct, yeah. But then how many, what is the thickness of this final vector? M, right? So this stuff here goes as thick as M, right? And so this is where we left last time, right? But then someone asked me, then I realized, so we have here as many as the different colors, right? So for example, in this case, if I just draw to make sure we understand what's going on, you have the first thing here, then you have the second one here, and then you have the third one, right? In this case. All right, so last time someone asked me at the end of the class, so how do we do convolution when we end up in this situation over here? Because here we assume that my kernels are just, whatever k long, let's say 3 long, but then they are just one little vector, right? And so someone told me, then what do you do from here? Like, how do we keep going? Because now we have a thickness. Before we started with a something here, this vector, which had just n elements, right? Are you following so far? I'm going faster because we already seen these things. I'm just reviewing. But are you with me until now? Yes, no? Yes, okay, fantastic. So let's see how we actually keep going. So the thing I just showed you right now is actually assuming that we start with that long vector, which was of height, what was the height? N, right? But in this case, also this one means that we have something that looks like this. And so you have basically here, this is 1, this is also 1. So we only have a monophonic signal, for example. And this was n, the height, right? All right, so let's assume now we are using a stereophonic system. So what is going to be my domain here? So, my x can be thought as a function that goes from the domain to the r number of channels. So what is this guy here?
One dimensional.
Yeah, x is one dimension in somewhere. So what is this omega? We have seen this slide, the last slide of Tuesday lesson, right?
Set of real values.
Say again?
Set of real numbers. R.
Omega is not set of real numbers. No, someone else tries. We are using computers. It's timeline, yes, and how many samples you have one sample number 2, sample number 3. So you have basically a subset of the natural space, right? So this one is going to be something like 0, 1, 2, so on, set, which is going to be subset of n, right? So it's not R. R is going to be if you have time continuous domain. What is C in this case? In the case I just showed you.
Number of output channels.
So far, what is C in this case?
Number of output channels.
Number of?
Output channels.
input channels, because this is going to be my X, right? This is my input. So in this case, we show so far, in this case here, we're just using one. So it means we have a monophonic audio. Let's have now the assumption, make the assumption that this guy instead is going to be 2, such that you're going to be talking about stereophonic signal, right? Okay, so let's see how this stuff changes. So in this case, my, let me think. Yeah, so how do I draw? I'm going to just draw, right? Complain if you don't follow. Are you following so far? Yes, because if I watch my tablet, I don't see you, right? So you should be complaining if something doesn't make sense, right? Otherwise it becomes boring if I'm waiting and watching you all the time, right? Yes? No? Yes, okay, I'm boring. Okay, thank you. All right, so we have here this signal, right? And then now we have some thickness. In this case, what is the thickness of this guy? C, right? So in this case, this one is going to be C. And in the case of the stereophonic signal, you're going to just have 2 channels, left and right. And this one keeps going down, right? All right. So our kernels, if I'd like to perform a convolution over this signal, right? So you have different samples here, right? And so on, right? If I'd like to perform a convolution, 1D convolution, I'm not talking about 2D convolution, right? Because they are still using a domain, which is here, number 1, right? So this is actually important. So if I ask you what type of signal this is, you're going to be basically, you have to look at this number over here, right? So we are talking about one-dimensional signal, which is one-dimensional domain, right? 1D domain. Okay? So we are still using a 1D signal, but in this case it has, you have 2 values per point. So what kind of kernels are we going to be using? So I'm going to just draw it. In this case, we're going to be using something similar like this. So I'm going to be drawing this guy. Let's say I have K here, which is going to be my width of the kernel. But in this case, I'm going to be also have some thickness in this case here. Right? So basically, you apply this thing here. Okay? And then you can go second line and third line and so on, right? So you may still have like here M kernels, but in this case you also have some thickness which has to match the other thickness, right? So this thickness here has to match the thickness of the input size. So let me show you how to apply the convolution. So you're going to get one of these slices here. And then you're going to be applying this over here. Okay? And then you simply go down this way. All right? So whenever you apply this, you perform this guy here, the inner product with this over here, what do you get? It's actually a 1 by 1, it's a scalar. So whenever I use this orange thingy here on the left hand side, and I do a dot product, a scalar product with this one, I just get a scalar. So this is actually my convolution in 1D. The convolution in 1D means that it goes down this way, and only in one way, that's why it's called 1D. But I will multiply each element of this mask times this guy here, and then you have second row and this guy here, okay? You multiply all of them, you sum all of them, and then you get your first output here, okay? So whenever I make this multiplication, I get my first output here. Then I keep sliding this kernel down, and then you're going to get the second output. third out, fourth, and so on until you go down at the end. Then what happens? Then happens that I'm going to be picking up different kernel. I'm going to get, let's say I get the third one. Okay, let's get the second one. I get the second one, and I perform the same operation. You're going to get here this one. Actually, let's actually make it like a matrix. You go down, okay? Until you go with the last one, which is going to be the mth, right? The mth kernel. Which is going to be going down this way. You get the last one here. Okay? Yes, no, confusing, clearing. So this was the question I got at the end of the class. Yeah, Tuesday. Yeah.
Why does the dot product return a single value, not one for each channel?
Because it's a dot product of all those values between. So basically, you do the projection of this part of the signal onto this kernel. So you'd like to see what is the contribution, like what is the alignment of this part of the signal onto this specific subspace. Okay, this is how convolution works when you have multiple channels. So far, I show you just with single channel. Now we have multiple channels. Okay, so oh yeah.
Is it possible to like see what this would look like for a 2D domain?
Yeah, in 1 second.
In this case, since you didn't pad, you're going to lose two values at the top and two values at the bottom, right?
One at the top, one at the bottom. So you actually lose the first row here, and you lose the last row here. So at the end, in this case, the output is going to be n minus 3 plus 1. So you lose 2. 1 on top. Okay, in this case, you lose 2 at the bottom. If you actually do a center, the convolution, usually you lose 1 at the beginning, 1 at the end. Every time you perform a convolution, you lose the number of the dimension of the kernel minus 1. You can try. If you put your hand like this, you have a kernel of 3. You get the first one here that is matching. Then you switch 1, and then you switch 2, right? So, okay, with 5, let's have a kernel of 2, right? So you have your signal of 5, you have your kernel with 2. You have 1, 2, 3, and 4. So you started with 5, and you end up with 4, because you use a kernel size of 2. If you use a kernel size of 3, you get 1, 2, and 3. So you lost 2 if you use a kernel size of 3, okay? So you can always try to do this. All right, so I'm going to show you now the dimensions of these kernels and the outputs with PyTorch. Okay? Yes? No? All right, cool. Okay, disaster. Can you see anything? Yes, right? Let me zoom a little bit more. Okay, so right now we can go, we do conda, activate, and then we have activate, yeah, PDL, right? PyTorch Deep Learning. So here we can just run IPython. If I press Control L, I clear the screen, and we can do import torch. Then I can do from torch import nn. So now we can see, for example, conv. Let's have my convolutional layer is going to be equal to nn conv. And then I can keep going until I get this one. Let's say I have no idea how to use this function. I just put a question mark, I press enter, and I'm going to see here now the documentation. Okay. So in this case, you're going to have the first item is going to be the input channel, then I have the output channels, then I have the kernel size. All right. So for example, we're going to be putting here input channels. We have a stereo signal, so we put 2 channels. The number of kernels, we said that was m, and let's say we have 16 kernels. So this is the number of kernels I'm going to be using. And then let's have a kernel size of what? The same I use here. So let's have k, or the kernel size equal 3. Okay? And so here I'm going to define my first convolution object. So if I print this one, conv, you're going to see we have a convolution, a 2D convolution, sorry, 1D convolution, my bad. Okay, so we have a 1D convolution, which is going from 2 channels, so a stereophonic, to a 16 channels, means I use 16 kernels. Okay, the kernel size is 3, and then the stride is also 1. Okay, so in this case, I'm going to be checking what is going to be my convolutional weights. What is the size of the weights? How many weights do we have? How many planes do we have for the weights? 16, right? So we have 16 weights. What is the length of the kernel? Okay. Oh, what is this too? Channels, right? So I have 16 of these kernels which have thickness 2 and then length of 3, okay? Makes sense, right? Because you're going to be applying each of these 16 across the whole signal. So let's have my signal now. It's going to be equal torch.rand n of size, I don't know, let's say 64. I also have to say I have a batch of size 1. So I have a batch of size 1, so I just have one signal. And then this is going to be 64. How many channels we said this has? 2, right? So I have one signal, one example, which has 2 channels and has 64 samples. So this is my X. Hold on, what is the convolutional bias size? It's 16, right? Because you have one bias per plane, per weight. Okay, so what's going to be now my convolution of X, the output? Hello? So I'm going to still have one sample, right? How many channels? 16. What is going to be the length of the signal? Okay, that's 62, okay? Fantastic. All right, so what if I'm going to be using a convolution with size of the kernel 5? What do I get now? You have to shout, I can't hear you. 60, okay, you're following. So, fantastic. Okay, so let's try now instead to use a hyperspectral image with a 2D convolution, okay? So I'm going to be calling now my convolution here. It's going to be my, in this case is correct, it's going to be a conv2D. Again, I don't know how to use it, so I put a question mark. And then I have here input channel, output channel, kernel size, stride and padding. Okay, so I'm going to be putting input channel. So it's a hyperspectral image with 20 planes. So what's going to be the input in this case? 20, right? Because you start from 20 spectral bands. Then we're going to be inputting the output number of channels. Let's say we're going to be using again 16. In this case, I'm going to be inputting the kernel size. Since I'm planning to use, okay, let's actually define my signal first. So my X is going to be a torch.rand, and let's say one sample with 20 channels of height, for example, I guess 128, well, hold on, 64, and then with 128, okay? So this is going to be my input data, okay? So my convolution now, it can be something like this. So I have 20 channels from input, 16 are my kernels I'm going to be using. Then I'm going to be specifying the kernel size. In this case, let's use something that is like 3 times 5, okay? So what is going to be the output? What are the kernel size? Anyone? Yes, no, what?
20 cross 16 cross 3 cross 5.
No?
So 20 channels stay, right?
20 channels is the channels of the input data, right? So you have how many kernels here? 16, right? there you go. You have 16 kernels, which have 20 channels, such that they can lay over the input 3 by 5, right? Thin, like short, short but large. Okay, so what is going to be my convolution on X sized? (116, 62, 124). Let's say I'd like to actually add back the, I'd like to have the same dimensionality. I can add some padding, right? So here there's going to be the stride. I'm going to have a stride of 1. Again, if you don't remember the syntax, you can just put the question mark and you figure out. And then how much stride should I add now? How much stride in the y direction? Sorry, yes. How much padding should I add in the y direction? 1, because it's going to be 1 on top, 1 on the bottom, but then on the x direction? 2. Okay, you're following. Fantastic. And so now if I just run this one, you're going to get the initial size. Okay? So now you have both 1D and 2D. The point is that what is the dimension of a convolutional kernel ensemble for 2D dimensional signal? Again, I repeat, what is the dimensionality of the collection of kernels used for 2-dimensional data? Say again? 4, right? So 4 is going to be the number of dimensions that are required to store the collection of kernels when you perform 2D convolutions.
What is the 1 exactly? Is that like...
The 1 is going to be the stride. So if you don't know how this works, you just put a question mark and you're going to tell you here. So stride is going to be telling you stride off. You move every time the kernel by 1. If you add the...
For the torch, that's size.
The first one means it's the batch size. So Torch expects you to always use batches, meaning how many signals you're using, just 1, right? So that's our expectation. If you send an input vector, which is going to be input tensor, which has dimension 3, is going to be breaking and complain. Okay, so we have still some time to go in the second part. All right, second part is going to be, so you've been computing some derivatives, right, for the first homework, right? So the following homework, maybe, you have to compute this one. Okay. You're supposed to be laughing. It's a joke. Okay, there you go. Fantastic. So this is what Jürgen wrote back in the 90s for the computation of the gradients of the LSTM, which are going to be covered, I guess, in next lesson somehow. So they had to still do these things, right? It's kind of crazy. Nevertheless, we can use PyTorch to have automatic computation of these gradients. So we can go and check out how this automated gradient works, okay? All right, so... All right, so we are going to be going now to the notebook number 3, which is the invisible. Let me see if I can highlight it. No, it's even worse. Okay, number 3, autograd tutorial. Okay. Let me go full screen. Okay. So autograd tutorial. What's gonna be here? Here I just create my tensor, which has as well these required gradients equal true. In this case, I've been asking Torch, please track all the gradient computations, the computation over the tensor, such that we can perform computation of partial derivatives. Okay. In this case, I'm going to have my y is going to be, so x is simply going to be 1, 2, 3, 4. The y is going to be x subtracted number 2. Okay. All right, so now we can notice that there is this grad fn function here. So let's see what this stuff is. We go sit there and see, oh, this is a sub backward. What is it? Meaning that the y has been generated by a module which performs the subtraction between x and 2, right? So you have x minus 2. Therefore, if you check who generated y, well, there is a subtraction module, okay? So what's going to be now the grad function of x? And you're supposed to answer. Oh, okay. Why is none? Because they should have written their Alfredo generated that, right? Okay. All right. None is fine as well. Okay, so let's actually put our nose inside. We were here. We can actually access the first element. You have the accumulation. Why is the accumulation? I don't know, I forgot. But then if you go inside there, you're going to see the initial vector. The initial tensor we are using is the 1, 2, 3, 4, okay? So inside this computational graph, you can also find the original tensor, okay? All right, so let's now get the z, and z is going to be my y squared times 3, and then I compute my average. A is going to be the mean of z, right? So if I compute the square of this thing here, and I multiply by 3, and I take the average, so this is the square part times 3, and then this is the average, okay? So you can try it if you don't believe me. All right, so let's see how this thing looks like. So I'm going to be plotting here all these sequence of computations. So we started from a 2 by 2 matrix. What was this guy here, 2 by 2? Who is this? X, okay, you're following, cool. Then we subtracted 2, right? And then we multiply by y twice, right? That's why you have 2 arrows. So you get the same subtraction, that is the y, the x minus 2, multiplied by itself. Then you have another multiplication. What is this? Okay, multiplied by 3, and then you have the final, the mean backward, because it's, why is green? Because it's mean. No, okay. Yeah, thank you for laughing. Okay, so I compute backprop, right? What does backprop do? What does this line do? I want to hear everyone. You know already. We compute what? Gradients, right? So backpropagation is how you compute gradients. How do we train neural networks? With gradient descent, right? Or whatever Aaron said yesterday. Backpropagation instead is used for computing the gradient. Completely different things, okay? Please keep them separated. Don't merge them. Everyone, after a bit, they don't see me, those two things keep colliding into one mushy thought. Don't. It's painful. Okay. Here I compute the gradients, right? So guess what? We are computing some gradients now. Okay, so we go on new page. A is going to be what? What was A? A was the average, right? So this is 1/4, right? The summation of all those zi's. Okay? So I goes from 1 to 4. Okay? So what is zi? Zi is going to be equal to 3yi squared, right? Yeah? No? Questions? No. Okay. All right. And then this one was equal to 3 times x minus 2 squared, right? So A, what does it belong to? Where does A belong to? What is the R, right? So it's a scalar. Okay. All right. So now we can compute dA over dx. So how much is this stuff? You're going to have 1/4, comes out from here. And then you have, let's have this one with respect to the xith element, okay? So we're going to have this one. I plug inside the zi, I have the 3yi squared, and this is going to be 3xi minus 2 squared, right? So this 3 comes out here. The 2 comes down as well. And then you multiply by xi minus 2, right? So far it should be correct. Okay, fantastic. All right, so my x was this element here. Actually, let me compute as well this one. So this one goes away, this one becomes true. This is 1.5 times xi minus 3, right? minus 2, minus 3.
Depends on how you run it.
Okay, mathematics, okay. Okay, thank you. All right, so what's going to be my dA over dx? I'm actually writing the transpose directly here. So for the first element, you have 1. You have 1 times 1.5, so 1.5 minus 3, you get 1 minus 1.5, right? Second one is going to be 3 minus 3, you get 0, right? This is 3 minus 3. Maybe I should write everything, right? So you're actually following. So you have 1.5 minus 3. Then you have 3 minus 3. Below you have 4.5 minus 3. And then the last one is going to be 6 minus 3. Which is going to be equal to minus 1.5, 0, 1.5, and then 3, right? You agree? Okay. Let me just write this one here. Okay, just remember. So we have already computed the back propagation here. I'm going to just print the gradients and then, ta-da, right? It's the same stuff we got here, right?
Why did you write it as partial derivative of A with respect to x and transpose?
So that's that I don't have to transpose it here. Whenever you perform the partial derivative in PyTorch, you get the same shape as the input dimension. So if you have a weight, whatever dimension, then when you compute the partial, you still have the same dimension. They don't swap, they don't turn, okay? They just use this for practicality. The correct version, I mean, the gradient should be the transpose of that thing. Sorry, the Jacobian, which is the transpose of the gradient, right? If it's a vector, but this is a tensor, so whatever. We just use the same shape thing.
I had a doubt whether this would remain same. Like in case of vectors, I know that.
No, so this one should be flipping, I believe. Maybe I'm wrong, but I don't think. All right, so cool. This is like basic. This is basic PyTorch. Now you can do crazy stuff because we like crazy, right? I mean, I do. I think if you like me, you like crazy too. Right? Okay. So here I just create my vector x, which is going to be a three-dimensional, a one-dimensional tensor of 3 items. I'm going to be multiplying x by 2, then I call this one y. Then I start my counter to 0, and then until the norm of the y is below 1,000, I keep doubling y, okay? And so you can get like a dynamic graph, right? The graph is conditional to the actual random initialization, which you can't even tell because I didn't even use a seed. So everyone that is running this stuff is going to get different numbers. So these are the final values of the y. Can you tell me how many iterations we run?
The mean is still less than 1,000, so it must be over.
So the mean of this stuff is actually lower than 1,000, yeah? But then I'm asking whether you know how many times this loop went through. No. Good. Why? It's random, right? So it's bad question. Okay, about bad questions, next time I have something for you. Okay, so I'm going to be printing this one. Now I'm telling you the grad are 2048, right? Just check the central one for the moment, right? This is the actual gradient. So can you tell me now how many times the loop went on? So someone said 11. How many? Hands up for 11. Okay, 4 people just rose their hands. What about the others?
21.
21. Okay. Any other guess?
Sorry, yeah, 11.
11. 10. Okay, we have actually someone that has the right solution. And this loop went on for 10 times. Why is that? Because you had the first multiplication by 2 here, and then the loop goes on over and over and multiplies by 2, right? So the final number is going to be this number of iterations in the loop plus the additional additional multiplication outside, right? Yes? No? You're sleeping? Maybe? Okay. I told you not to eat before class, otherwise you get groggy. Okay, so inference. This is cool. So here I'm going to be just having both my x and y. We are going to just do linear regression, right? Linear whatever thing. The at operator is just the scalar product, okay? So both the x and w have the required gradient equal to true. This means we are going to be keeping track of the gradients and the computational graph. So if I execute this one, you're going to get the partial derivatives of the inner product with respect to the input is going to be the weights, right? So the range is the input, right? And the ones are the weights. So partial derivative with respect to the input is going to be the weights. Partial with respect to the weights is going to be the input, right? Yes, no, yes, okay. Now I just, usually it's this one is the case. I just have required gradients for my parameters because I'm going to be using the gradients for updating later on the parameters of the model. And so in this case you get none. Let's have in this case instead what I usually do when I do inference. So when I do inference, I tell Torch, hey Torch, stop tracking any kind of operation. So I say, Torch, no grad, please. So this one, regardless of whether your input or weights have the required grads true or false or whatever, when I say Torch, no grads, you do not have any computational graph taken care of, right? Therefore, if I try to run backpropagation on a tensor which was generated from, like doesn't have actually, a graph, because this one doesn't have a graph, you're going to get an error, okay? So if I run this one, you get an error, and you have a very angry face here, because it's an error. And then it tells you element 0 of tensor does not require grads, and does not have a grad function, right? So E, which was the, whatever the Z here actually, the Z, you couldn't run backprop on Z because there is no graph attached to Z, okay? Questions? This is so powerful. You cannot do this stuff with TensorFlow, okay? TensorFlow is like, whatever, yeah. More stuff here, actually more stuff coming right now. So we go back here, we have inside the extra folder, you have some nice cute things. I wanted to cover both of them, just that we go just for the second, I think. So the second one is going to be the following. So in this case, we are going to be generating our own specific modules. So let's say I'd like to define my own function, which is super special, amazing function. I can decide if I want to use it for, training nets. I need to get the forward pass and also have to know what is the partial derivative of the input with respect to the output, such that I can use this module in any kind of, point in my, code, such that, by using backprop, chain rule, you just plug the thing. No, Jan went on several times. As long as you know partial derivative of the output with respect to the input, you can plug these things anywhere in your chain of operations. So in this case, we define my addition, which is performing the addition of the two inputs in this case. But then when you perform the backpropagation, if you have an addition, what is the backpropagation? So if you have an addition of the two things, and you get an output, when you send down the gradients, what does it happen with the gradient? It gets, copied over both sides, right? And that's why you get both of them are copies of the same thing, and they are sent through one side or the other. You can execute this stuff. You're going to see here you get the same gradient both ways. In this case, I have a split. So I come from the same thing, and then I split, and I have those two things doing something else. If I go down with the gradients, what do I do?
We add.
You add them, right? And that's why we have here the add. And so you can execute this one. You're going to see here that we had these two initial gradients here. And then when you went up, when you went down, the two gradients sum together. And they are here, okay? So again, if you use pre-made things in PyTorch, they are correct. This one you can mess around, and you can put any kind of different, forward function and backward function. I think we are out of time. Other questions before we actually leave? No? All right. So I see you on Monday, and stay warm. Bye-bye.